Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, we've come to the last part of this lecture on NMR, and this is something which is complementary as how this type of NMR is also complementary to the main NMR topics that we have discussed so far. So far we have covered on proton NMR, and that's the main part of this syllabus to actually understand proton NMR and what it can do, and also NMR as a whole, how the NMR functions on different aspects on the understanding the molecular structure, and using that also for the dynamic processes. And of course there are so many other things that you have yet to explore, and you can still explore even though it's not part of the syllabus. You can have that that you can read a lot of this NMR application, which even it's very useful even for our daily lives activities and investigation as well. So of course there are different types of NMR in terms of the nucleus that you can actually study, but the one that we touch mainly was on proton or hydrogen NMR. So there are, most of the times the examples given are all very simple, straightforward NMR spectra. So that's for the to understand NMR pedagogically, so that you can build up the knowledge, so you understand that different chemical shapes will actually address the different what you call functional groups and so on. But there are times when, especially when you're doing research, you're faced with complexity, this complex NMR spectrum, and so the interpretation and analysis can be very, very challenging. And so that, and especially when there are actually overlapping spectral lines. So when you have overlapping spectral lines, it's no more an AX system. So A and X, they are far apart in terms of the alphabets. So when you have an AB system, spin system, so A and B are very close together alphabetically. So that is to show that, you can have this complexity, and so you can have this overlapping. So how do you actually interpret that? So that even within the context of proton NMR, there are actually different ways to actually do things. But one of the other things that you can actually do, because most of this what you call molecules consist of hydrocarbons, so you can look at, you can have a complementary as a complementary tool to proton. You can look at another type of nucleus to focus on. So let's talk about how you can actually simplify complex NMR. So one of the things that you can actually do is actually use a high magnetic field strength. So that means that if you have a 300 megahertz spectrometer, then use a 400 megahertz spectrometer so that you can have better resolution, or maybe 600, to have a much better resolution. But of course, that is cost. Okay, you can't immediately say that, okay, let's use a 400 and a 600 megahertz, for example, instead of 300. Sometimes the machines are not available, so you have limited resources. And of course, if you want to purchase, it's not, a one-day purchase. The process is long, so that may not be an immediate clever way to actually simplify the complex. So of course, this is just to emphasize that if you have a very strong magnetic field, so you have this better resolution, so you don't have this crowded molecule there. But let's talk about this, what do you call, this, the other way, the cleverer way to actually do things. So this thing that this is suggested here is to the spin decoupling or double resonance experiment. So what it means is that the sample that you want to analyze is irradiated at a certain frequency to either eliminate fully or partially the effect of coupling between certain nuclei. So you don't want that the coupling between you don't want the coupling, the spin-spin coupling to exist. So you just focus on this, what do you call, this, the carbon 13. Okay, so this is called the spin-spin decoupling. Okay, so in this case, we have this acetaldehyde. So when you have the proton NMR, so we have here the proton here. You have this multiple peaks due to the methyl group here, and the methyl group here is a doublet due to the proton here. So if you actually do the carbon 13, so you have here just peaks for the carbon. So there's no coupling, so you know that you expect only 2 carbons there, and you see that only that. And so that simplifies things, especially when you have a bigger molecule. So at least you know that your molecule has a certain number of carbon, and that's the number of peaks that you should have for the respective carbons. So of course there are there are various ways, as I said, the amount of experiments that you can actually do on the NMR, just the default program in there, and also the program that you can add, the pulse program that you can actually write there. You can code yourself, write a computer code on the computers, on the computers of the NMR that control the machine. So you can have that very specific experiment. But even on the spin decoupling, there are various types of decoupling that you can actually do. Okay, and the things that we're talking here is on the heteronuclear between the carbon and the hydrogen here. Now I'm not going to talk in details on this particular carbon 13 NMR, but I just want to tell you that on certain situations when you have complexity, they are not limited to this. There are various types of experiments that you can do on top of the main proton NMR to actually to verify to verify concretely the structure they have. This is especially when you have a very complicated molecule that you want to determine the molecular structure. You can also have the 2D NMR to double confirm also on the molecular structure. So in terms of you do this decoupling experiment, of course the advantage is that you simplify the spectra, the resolution, and you sort of like make the multiplex within singlet. So that's sort of like no more overlapping, and you have this enhancement in signal to noise ratio. But of course, with all this simplifying, you're losing the multiplex structure, and so you sort of like lose important information. But again, this is a complementary experiment. So this is something that you add on to whatever experiment that you do, the proton NMR, to further confirm what you have. Okay, and so you have this carbon 13, as I said, which uses the proton decoupling. So it falls under the hetero decoupling method. And because it has 1% of natural abundance, so you need a good amount of sample to actually run this. And this is only for carbon 13 because carbon 12 is NMR inactive. Okay, and this also carbon 13 has a spin half. Has a spin number of half. So this is less sensitive, so it's not as strong as the proton. And the chemical shift range is quite large, also measured with respect to TMS. And whatever factors that affect the chemical shift will also affect the proton NMR. Sorry about that. So the number of beats will also indicate the number of the types of carbon that you have. So you have this the resonance due to carbon 13 are split by this neighboring proton. I'm losing my voice here. So then this coupling is removed by having a second radio frequency. And so once you remove that second frequency, then you only see the single line of the carbon. Now I'm sharing with you, now this is not the only video available in YouTube, but this is one video that I like due to its simplicity of explaining on the carbon 13, and I would recommend you to watch this, and so you understand that it's not anything different from the way the NMR is being done from proton NMR, but in terms of interpretation, it's just to show that it also depends on the types of carbon that's available. So you have the carbons, the chemical shift of carbon represent for that of different functional group. Okay, so do watch that. Okay, and so that sort of like wraps up what we have covered on the NMR aspect. So do watch all the videos that's been shown and the notes, and so we'll discuss further on what we're going to talk the next time. All right, so take care, and Assalamualaikum warahmatullahi wabarakatuh.